أفمن يعلم أنما أنزل إليك من ربك الحق كمن هو أعمى إنما يتذكر أولو الألباب. تلك آيات الكتاب والذي أنزل إليك من ربك الحق ولكن أكثر الناس لا يؤمنون. الله الذي رفع السماوات بغير عمد ترونها ثم استوى على العرش وسخر الشمس والقمر كل يجري لأجل مسمى يدبر الأمر يفصل الآيات لعلكم بلقاء ربكم توقنون.
Before the atom excitation ended, giving a negative value and making it appear as if the photons had exited the material before entering it. These results suggest that negative values of time, such as the group delay, have more physical significance than is generally accepted, the researchers wrote. The results are detailed in a paper titled Experimental Evidence that a photon can spend a negative amount of time in an atom cloud, which is still awaiting peer review. Experimental quantum physicist Ephraim Steinberg of the University of Toronto wrote in X, "It took a positive time, but our
The paper comes from Ephraim Steinberg's group in Toronto. They measured photons, so the quanta of light, as they pass through a medium. To understand the business with the negative time, we first have to talk about what a photon is. You might think that a photon is a single wave, but that would mean that it extends all through space. The photons that we use in the laboratory aren't like that. They are instead what we call a wave packet. That's a lot of individual waves with different wavelengths on top of each other so that they combine to a neat peak. The important thing is that even a single quantum of light contains different wavelengths. The next thing you need to know is that the velocity by which such a wave packet moves isn't necessarily the same as that by which the individual waves move. We measure the velocity of a single wave by how fast the crest or trough travels. That's called the phase velocity. But if we're looking at a wave packet, we usually look at the velocity of the average, called the group velocity. The group velocity can be slower or faster than the phase velocity. Indeed, the wave packet can even go into the opposite direction than the individual waves. This is called a negative group velocity. These differences between the phase velocity and the group velocity happen if the photon goes through a medium that affects different wavelengths differently. Now imagine you take a wave packet that goes into a medium and back out, but the medium distorts the package so that it amplifies the first half of the package and suppresses the second. It can then happen that actually the peak of the outgoing package appears before that of the ingoing package has disappeared. If you think of the wave packet as one big signal, that doesn't seem very remarkable. Okay, something weird is going on in that medium which distorts the package, whatever. But if you think that the wave packet describes one quantum of light, it now seems that the quantum came out of the medium before it went in. This is called a negative group delay or a negative time, and this is what the new paper is about. This negative time has been observed previously for light and also sound, but how it works at the quantum level, no one really understands. And this is what the new experiment now looked into. You see, if a quantum of light enters a medium, then it'll usually get temporarily absorbed by some atoms and then re-emitted. Just what happens can depend on the wavelength of the light, and in particular, it can shift the phase of the light. This is what leads to all these strange distortions of the wave packet. In this new experiment, they sent photons into a cloud of rubidium atoms, which causes a negative group delay. By carefully tracking what the atoms do, they reconstructed the phases of the individual photons with and without the cloud. They find that the phases of the photons are shifted into the direction that they're traveling. It's a negative delay, like you're pushing forward a photon. You can see in this figure that compared to the reference case, the shift doesn't just correspond to an immediate release, which would be zero delay, but actually to a negative time. In the abstract, they say that these results suggest that negative values taken by time, such as the group delay, have more physical significance than has generally been appreciated. Really? Well, first of all, this negative time has nothing to do with the passage of time. It's just a way to speak about how a bunch of photons travel through a medium and how their phases shift. Second, you can convince yourself mathematically that this so-called negative time or negative group delay doesn't lead to violations of causality, and information still can't be sent faster than the speed of light in vacuum. It's one of those cases where something sounds really weird at first sight, but the more you think about it, the less weird it gets. None of this is to say that the experiment isn't interesting. Understanding how negative group delay works has a practical use. It's because signals that travel in optical fibers and other media can get distorted due to group delay, and you can correct for that by putting in